Let's do another example, but this time we're going to use that formula that we had just learned, the universal the universal gravitation formula, to solve for the different variables. So in this example, we have object A exerting a gravitational force of magnitude 6.3 times 10 to the negative 9 newtons on object B. The question wants us to solve for object A having a mass of 6 kilograms and object B having a mass of 9.5 kilograms. What is the distance between the two objects? So let's first write out what we know. We know that there's a force due to gravity, or it's pulling it with a force of 6.3 times 10 to the negative 9 newtons. We also know that the mass of object A is 6.0 kilograms. The mass of object B is 9.50 kilograms. And it wants us to find what is the distance between. What is this R? Looking here, we're going to use our formula that Fg is equal to the gravitational constant times ma mb over r squared. Alright, so looking back here, I've jumped a few steps on the last example, so I'll explain things a little better. When we gave our formula before, we had Fg with these two lines beside it. Remember, that just means the magnitude. You can include those if you want. All it's going to tell you is when you get your answer, if you get a negative number, just make that number positive. It just means your answer is always going to be positive. Again, G is the gravitational constant. Before we had M1 and M2. That doesn't matter. I've just relabeled these MA and MB because that's the way it was given to us. You can make them M1 and M2 if you want. It's just a placeholder, or not a placeholder, but a different symbol to represent the same thing. And r squared. So this r squared is what we are wanting to solve for. We're wanting to find the distance between the two objects. So to do that, I'm going to multiply both sides by r squared. When I do that, that's going to cancel out those and leave us with r squared times Fg is equal to G, Ma, and B. Now we want to get this r squared by itself though. So I'm going to divide both sides by the force due to gravity. So if I rewrite this to make it a little neater, now we have r squared is equal to G, Ma, mb over Fg. Good. So now to get this r by itself, either squaring it, the opposite of squaring is finding the square root. If we do it to one side, we have to do it to the other. So now we finally have our formula. This is going to cancel out, and we're going to have r is equal to the square root of the gravitational constant times the mass divided by the force due to gravity. So if I go ahead and start plugging in my numbers for that, we have r is equal to our gravitational constant, 6.67 times 10 to the negative 11 Newton meters squared over kilograms squared times mass A, 6.00 kilograms, times mass B, 9.50 kilograms, divided by the force due to gravity, which in this case is 6.3 times 10 to the negative 9 newtons. Now once you've done all that, don't forget that you need to take the square root of your whole answer. If you forget to take that square root, you're not going to get the distance between, you're going to get the distance between squared. So once you've plugged that all in, you're going to find the distance between object A and object B to be 0.78 meters. So let's try this again, but what happens if object A and object B have equal masses? So now we are just taking the information from up here. We just know the gravitational force. All this other information where object A had a mass of 6 kilograms and object B had a mass of 9.5 kilograms, we're not going to include that in part B. We're just doing the information above. So, in part B, object A and object B have equal masses and are placed 7.25 meters apart. Find the mass of each object. So again, I like to write down everything I know. In this case, our force due to gravity was given above, and that is 6.3 times 10 to the negative 9 newtons. We also were given what our distance between the objects is, and that is 7.25 meters. And our question wants us to find the mass of the two different objects. But what we know is object A and object B are equal to each other. They have equal equal masses. So MA is equal to MB. That's what we're trying to figure out. So to do that, if they're equal, we can combine them, and they are now equal to mass squared. Right? Mass, or something times itself, is squared. It is not 2 times m, which is a common mistake. Right? You're not multiplying the mass by 2, you're multiplying the mass by itself. So it's not 2m. Alright, so using our formula, we have Fg is equal to g m1 m2 divided by r squared. But remember, since these masses are both the same and we are multiplying them together, we can have g is equal to m squared over r squared. We are just multiplying it by itself, so it's squared. Now we can rearrange and solve for mass. So I'm going to go through this pretty quickly, but if you need help going through how to rearrange the formula, please let me know. So when you rearrange, mass is going to be equal to the square root of Fg times r squared over the gravitational constant. When we plug the information in, we have Fg is 6.3 times 10 to the negative 9 newtons. We have r squared, which is the distance between, 7.25 meters squared, divided by our gravitational constant, which is 6.67 times 10 to the negative 11 newton meters squared per kilogram squared. Again, don't forget to take your square root for all of that, so you can figure out your mass, not your mass squared. So when you plug this in, you're going to find that the mass is equal to 70.5 kilograms. That is going to be the mass for object A and the mass for object B. They are the same mass. Alright, the only time we can use this m squared is when they have equal masses. If they don't, we're going to use the first version of the formula. Let's do one last example to wrap up the topic. So an astronaut has a mass of 68.5 kilograms, and we want to determine the magnitude of the weight of the astronaut at that point on, for A, Earth's surface. So remember, the weight is the force due to gravity, right? If you see weight, that does not mean mass. So there's two ways we can solve this. The first way is if you know what the acceleration due to gravity is. We know on Earth the acceleration due to gravity, or g, is 9.81 meters per second squared. So to do that, all we need to do is what we've already been doing. We know the mass, in this case, is 68.5 kilograms. We know that the acceleration due to gravity is 9.81 meters per second squared. And we can use that to find Fg, which is just the force due to gravity is equal to the mass times the acceleration due to gravity, which is 68.5 kilograms times 9.81 meters per second squared. When you figure that out and solve, you're going to get an answer of 672 newtons. Again, this is still it's still a vector, so you need to include a direction. You can include a free body diagram and use negative 9.81 going down, or you can make that positive. But we know by common sense that this is going to be heading down. This is going to be heading towards the Earth. So I'm just going to call it down. Alright, that's if we know the gravitational constant. If we do not know it, so if G is not known, then we can't use this formula. Where G may not be known, it may be on a different planet. Maybe we are pretending like we don't know it's a constant of 9.81. Any example like that. So to figure that out, you're going to take your mass, or you're going to write down what you know. We have our mass of our object. Our mass is equal to 68.5 kilograms. We know it's being pulled down to the Earth. So the mass of the Earth is 5.97 times 10 to the 24 kilograms. That there is something that you're going to know, but it's also on your formula sheet. So where you would find it on your formula sheet is you would have the mass of the Earth is equal to 5.97 times 10 to the 24 kilograms. Under this section, you're also going to have your acceleration due to gravity. You're going to have your gravitational constants, which we've talked about. And you're also going to have the radius of the Earth. So that's the distance from the center of the Earth to the surface. That's important for us to know, right? That's the different distance between the object is being pulled, the distance between the center of the Earth and the object that's being pulled, or the astronaut which is on the surface. So that on our formula sheet again was 6.37 times 10 to the 6 meters. These here are on your formula sheet. You're not going to have to memorize them, but you are going to need to know where to find them, and you are going to have to use them. So our formula in this case is going to be Fg is equal to G m1 m2 divided by r squared. That gravitational constant formula. When we plug in, we know our gravitational constant, again, from our formula sheet, is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So we're going to have 6.67 times 10 to the negative 11 kilograms squared, Newton meters squared per kilogram squared, times mass 1, 68.5 kilograms, times mass 2, 5.97 times 10 to the 24 kilograms, divided by the radius, or the distance between from the center of the Earth to the surface, 6.37 times 10 to the 6 meters squared. When you plug this all into your calculator, you're going to get an answer of 672 newtons. Again, common sense will tell us this is pulling the human down, or the astronaut down, so the direction is going to be down. You'll notice you get the same answer, but it's just what is known. If you know G, great. If you don't know G, then you're going to have to